In this video, we're going to study the properties of discrete time Fourier transforms. So now what is Fourier transform? It's basically a map or a function from real number omega to a complex number x, right? Omega is a real number, but x is an imaginary, complex number. So all the properties of complex numbers apply to x e to the power j omega. So which means x e to the power j omega has a real part plus j times the imaginary part. Another representation for x e to the power j omega is the magnitude times the phase, basically e to the power j theta, where theta is the phase of x e to the power j omega, right? And the normal relations of complex numbers, which they also apply. For example, the real part is given by the complex number plus the conjugate divided by 2. The imaginary part is given by the complex number minus the conjugate divided by 2j. These are normal properties of complex numbers which you are all very much familiar with. Now the other representation is the polar representation. The magnitude of x e to the power j omega is given by these relations, basically the number times the number conjugate under root, or the real part square plus imaginary part square, right? These are the representations for the magnitude of x e to the power j omega. And now how do you find the phase of x e to the power j omega? For that, you see x imaginary upon x real, and then tan inverse of this. That is the phase of the complex number. So, okay, apart from these, the properties which are specific to x, the discrete time Fourier transform, one of the very important properties is that it is periodic with a period of 2 pi. So this is the general representation for x to the power j omega, like very general representation. Then what we notice here is, consider, let us say I do not write it as x e to the power j omega, but I write it as x omega, simply x omega. Okay, so let me first try to explain why do we write it as x e to the power j omega and not as x omega, right? Because of this property of periodicity. I want to say that my x of omega plus 2 pi k for any integer k, let us consider it as 1 for the time being, just for an example. This is equal to x omega, right? And to encode this property, or to make it very explicitly visible, I just write it as x e to the power j omega, because I know that now if I write x e to the power j omega plus 2 pi, then this is naturally equal to x e to the power j omega times e to the power j 2 pi, and as you know, x e to the power j 2 pi is 1, right? So it is equal to x e to the power j omega. So basically they are both are same. Now to prove that actually x e to the power j omega is periodic with 2 pi, let us consider this. This was just for the representation, but now the original thing is actually periodic. How do we prove that? So the formal proof is here. So consider x omega plus 2 pi k, assuming I do not know that this is periodic with omega. Now write down the form of basically this form. If I substitute the omega to be omega plus 2 pi k for any integer k, it looks like this. Now I can open it up. I can split x e to the power j omega n and j 2 pi k n. And now this part, this whole part is same as x e to the power j omega, but this part is equal to 1 pi because both k and n are integers. So x e to the power minus j 2 pi, any integer, is basically 1, right? So therefore this part is just x omega. So which means my discrete time Fourier transform is periodic. Since it is periodic, to make the periodicity explicitly visible, I write it as x e to the power j omega and not as simply x omega, right? Okay, so write it as x e to the power j omega. Okay, now so some new terms, conjugate symmetric and conjugate antisymmetric. So all of you know that any signal xn, if it is real, it can be decomposed into two parts, even part and the odd part, right? Where even part is such that my x of even part of n is equal to x of even part of minus n, right? And x of odd part of n is equal to minus x of odd part of minus n. Right? So you remember this is for real only, for real x only. So you remember that real part is something like, the even part is something like this, and the odd part is something like this. Right? This is odd, and this is even. So any real signal can be decomposed into even and odd parts. Okay. Similarly, now this x is a complex number. It's a complex sequence. So I define real and odd, even and odd in a different way. So I say the even part, I call it as conjugate symmetric part because it is the conjugate which is required because it is a complex number. So conjugate symmetric part is simply xe is equal to xe of n is equal to x star of minus n. So this is the definition of conjugate symmetric, and this is the definition of conjugate antisymmetric. So they are analogous to even and odd in the real domain, right? Now, how do I compute xen? It's very simple. Xe of n is simply x of n plus x star of minus n. You can substitute it back here and see that this property is satisfied. And x odd or x conjugate symmetric of n is equal to half of xn minus x star of minus n. You can put it back here and see that the property is satisfied. And similar can be done for the Fourier transform x e to the power j omega 2. Similarly, you can define xe and xo, right? And the same relations apply there too. Okay. Now let's discuss about the convergence properties of DTFT. Convergence. So for DTFT to exist, this sequence must converge, right? Okay, if it goes from minus infinity to plus infinity. Now let us define xk, where k is a finite number, right? K is an integer, and a finite integer, not infinity. You know that limit when the k tends to infinity, then this thing becomes the DTFT. But if k is not infinity, then let us call it as xk. Now the DTFT x e to the power j omega, it is said to converge uniformly, this new term, uniformly, if x e to the power j omega is same as the limit k going to infinity xk e to the power j omega. Right? If this limit exists, then this is called uniform convergence. X e to the power j omega is said to converge uniformly. Okay. So let us see, when does that happen? It will happen, okay, my x e to the power j omega can be written in this form, right? And I can say, now this thing is less than equal to the mod of the individual parts, like xn and e to the power minus j omega n. And you know that e to the power minus j omega n, the modulus is always 1. So this means if xn is less than is absolutely summable, which means if sum of the absolute value of xn over all n is finite, then I'm from this part, from this expression, so this part is 1, so it does not exist. But then I'm perfectly sure, since this part is finite, this part is less than equal to this, so this must be finite, right? If this is finite, then this is definitely finite, which means it does exist. So thus absolute summability of xn, this is absolute summability. This condition, if it is satisfied, this is sufficient for the existence of DTFT. And I'm sure that DTFT will certainly exist because this sum will be a finite sum. Okay, so there are exceptions. So remember that we discussed about the sufficient condition for the existence of DTFT, that is the absolute summability of xn, but still this is not the necessary condition. There are cases where the sum does not, basically the xn is not absolutely summable, but still DTFT exists. So, okay, Mostly we deal with xn's of finite length and finite sample values, so that is absolutely summable. So DTFT exists normally, but there are exceptions. There are certain weird xn which are not absolutely summable, but converge to the DTFT in the mean square sense. Okay, so this is one kind of exception, that they may not be absolutely summable, but still the DTFT exists. So what is mean square convergence? So we explain this concept with the help of an example. This example is, okay, we are starting with x e to the power j omega. Let us say this is x e to the power j omega, and this is omega. So what is the value of x e to the power j omega? It is 1 when omega lies between omega c and minus omega c, basically something like this. And pi is still far away. And so it is 0 everywhere else, but it is 1 between minus omega c and plus omega c. So this is like a band pass filter, or okay, you can call it as a low pass filter. So basically it's a filter. We will see it in the future very frequently. But for now, let us think of it as just a function. Okay, then this implies my corresponding xn, the inverse Fourier transform, will be this formula. Let us substitute values and find out. So it is 1 for minus omega c to plus omega c and 0 otherwise. So it reduces to this form, right? This is 1 into, okay. And then there are two cases possible, if n is 0 and if n is not 0. Let us say if n is 0, then this thing will become, whole thing will become 1. And this is just summation from minus omega c to plus omega c of 1, which is same as omega, so it's 2 omega c upon 2 pi, right? But if n is not equal to 0, the other possibility is that n is not equal to 0. In that case, the integration will be e to the power j omega n divided by jn, limits minus omega c to plus omega c, right? And if you compute it, it will be equal to this. So this is simply sine of omega c n upon pi n, right? So this is how the original signal looks like. So my x of n is, if n is not 0, it is a sinc function. This is called sinc function. Sinc of omega c n. And the denominator is, and the for n equal to 0, we have xn as simply omega c upon pi. Okay. Now, let's talk about mean square convergence. The dt of, if I start from this xn and try to compute its DTFT, it does not converge uniformly, which means my xk and x won't match even if capital K tends to infinity. So why does this happen? Let us try to plot it and see. So if I take my original xn and compute its DTFT, basically xk, so this is k. So for k equal to 1, it will be looking something like this. You remember your expression of xk, it will look something like this. But for k equal to 3, it will be something like this. If you keep increasing k equal to 7, k equal to 19, you see that it will become more and more like the omega 1 between minus omega c to plus omega c and 0 otherwise. But even if you make k very large, this portion at the corners, it will never become, the error will never become 0. Error will always remain finite. But means at these points, it will never become 0. This one will never become 1. There will always be a finite difference here. But in the mean square sense, what does that mean? The energy in these regions, the energy in this erroneous regions, this will converge to 0. So limit xk minus x whole square summed over omega from minus pi to pi, the limit it goes to 0. Basically the energy in this erroneous regions, it goes to 0. So let us say if the error occurs only in very small domain and everywhere else it converges, right? Yeah. So this gap becomes smaller and smaller, so much so that the energy in this becomes 0. Even if the magnitude is non-zero, the energy in it will be 0. So this is the mean square convergence. Another exception where the xn is neither absolute summable nor even square summable, but still the DTFT exists, right? That example is pure sinusoid. In case of pure sinusoid, you have e to the power j omega naught n, and you all have already computed what is the Fourier transform of this. Basically, the Fourier transform is a delta function, right? It peaks at omega naught, 2 pi plus omega naught, minus 2 pi plus omega naught, and in all the periodic windows. So this is another example where DTFT exists even if absolute summability is not obeyed, and not even square summability is obeyed.